All right, so organic chemistry is kind of a new field in science in terms of the grand scheme of things. Most fields of science like physics and biology go back to the 1700s, 1600s, about that time frame. Organic chemistry really was first developed in the mid-1800s. So prior to about 1830, they thought that certain compounds and molecules were derived from a vital source, meaning that they had some sort of special property to them, specifically something that made them useful for biological systems, right? So biomolecules, they thought, had some sort of special magical property to them, right? So they said that they were derived from a vital source. However, today we know that organic chemistry isn't that way. In fact, a lot of organic molecules aren't involved in living systems at all. So, for example, plastics. Plastics are organic compounds, but they're not involved in living systems. How do we describe organic chemistry today? Carbon, right? So modern just means that we're dealing with stuff that has carbon in it. It's one reason I like organic chemistry is if you look at the periodic table, really what we're looking at is carbon, nitrogen, oxygen, that top right-hand corner, along with hydrogen on the far left corner. So we're dealing with only a handful of elements that we can use to make a wide variety of compounds. All right, then the question is, well, why is carbon so special? Why do we have a whole branch of chemistry just for carbon? So I'll ask you, why is carbon special? Anybody want to throw out a suggestion or answer? Yeah. Ability to make rings. So can bond and form rings. We're going to spend a lot of time on rings this term. Anything else? Yeah.
It has the ability to make four bonds.
Yeah, that's a really cool property. Anything else? Think about biology. What are the main biomolecules that we're concerned with? It's really abundant. That's another one. So in biology, what are the main classes of biomolecules? DNA. Yeah, so nucleic acids, things like that, like DNA, RNA. What's some other ones? Carbohydrates, another one? Proteins, another one? Lipids. All of those have carbon backbones, right? So carbon is the backbone of biomolecules. Carbon is really fascinating too because it can bond in so many different ways. So the classic example I like to talk about is, what does it look like if you're holding just carbon? No other elements. What does it look like? Yeah, exactly. So some of you might have diamond rings, right? Diamond is carbon. Some of you have pencils. Graphite is pure carbon. Some of you may be familiar with graphene, right? Graphene is a infinite two-dimensional sheet of carbon. Really interesting stuff. Carbon nanotubes, some of you might have heard about. That's all carbon too. Carbon is incredibly versatile and can be used to make a wide variety of bonds, both single, double, and triple, or all three, I should say. All right, so let's talk about the father of organic chemistry. This guy. This is Gilbert Lewis. Gilbert Lewis is known for a wide variety of things in chemistry. Any of you familiar with his contribution to acid-base chemistry? Lewis acids and bases, right? So does anybody remember what a Lewis acid does? It accepts electrons. So we'll talk more about that later. Don't worry if you forgot acid-base stuff. But he's responsible for acid-base chemistry, understanding how electrons are moved in acid-base chemistry. But more importantly, he was the first to describe a covalent bond. What is a covalent bond? Not everybody all at once. Sharing electrons, right? So when we think about ionic bonds, that's an attraction between a cation and an anion, right? Covalent bonds mean we're now sharing electrons, no longer transferring. So it means to share, of 2 electrons. And I always show electrons as E-. It's just way faster than writing electrons. Between 2 atoms. Pretty fundamental discovery. Amazingly enough, he, I would argue, contributed a disproportionate amount of knowledge to the field of chemistry, and yet he got overlooked every single year for the Nobel Prize because he had an enemy on the Nobel Prize committee. Got a really fascinating life. If you are interested, I'd be happy to talk with you about him. Really interesting stuff, though. He wasn't the most likable guy, too, so that was another part of the reason why he never won a Nobel Prize. Yep.
It's connected to the Lewis dot.
Yes, exactly, and that was the next thing. So his next thing was that he came up with Lewis dot structures. It's like I paid you to say that. And Lewis dot structures are really important in organic chemistry, although we don't use them that frequently, or at least we don't think about them that frequently. All right, so let's take a look at Lewis dot structures in terms of valence electrons. All right, when you're drawing a Lewis dot structure, do you include all electrons? No. Which electrons do you include? Valence, right? So Lewis dot structures, you only include valence electrons. And if you remember back to general chemistry, valence electrons are the outermost electrons. They're the ones highest in energy, the most reactive electrons. The easiest way to remember the number of valence electrons is to look at the periodic table, ignore the numbers, focus on the Roman numerals, and column 1A means you have 1 valence electron. Column 2A means you have 2. Ignore the middle block, that's for inorganic chemists, and then hop over to 3A and say, all right, boron, yeah, 3 valence electrons, carbon, 4, and so on. It's really easy, just look at the periodic table. So like I said, hydrogen would have 1 valence electron, so you put 1 dot. Boron would have 3. This gets a little trickier when we have more than 1. Do I go 1, 2, 3? What should I do? Spread them out, yeah. So try to cover all 4 sides before pairing, right? So boron, we would have 3 dots around it. Try not to pair them unless you have to. Carbon, same thing. We go 1, 2, 3, 4. And then we could go to something like fluorine. Oops, sorry. Holy cow. Put an L in there. Fluorine should have 7. 1, 2, 3, 4, 5, 6, 7. And there you go. So Lewis dot structures are really essential. Organic chemists will oftentimes shorthand more complicated molecules, and we'll go over all the shorthand notations for organic chemistry later. The other important thing is that electrons like to be paired. Just like Gilbert Lewis saw that a covalent bond is 2 electrons, he noticed also that they tend to be paired even when they're not bonding too. So let's talk about the different ways they like to pair. We already said 1 to be a covalent bond. What happens if you have a pair of electrons that aren't participating in bonding? What do we call those? Lone pairs. Either way, they really, really like to be paired, whether they're in a bond or just hanging out on their own. There are exceptions to this. Does anybody know the exception? Radicals. So radicals are unpaired electrons. They tend to be very reactive, and in fact, we'll cover radical chemistry later on this year. All right, so let's practice some Lewis dot structure basics before we have to head out. All right. First one is pair electrons. Like I said, either as lone pairs or as bonding pairs between two atoms. The next one is pretty important. Atoms prefer to have 8 electrons around them. And the key with this is you count both electrons in a covalent bond. So that's key. That's the octet rule. I really hate the term rule because it is often not the case. We'll see that over and over and over again. It's an octet preference. Atoms are happiest if they have 8. All right. And then the last one before we head out is include formal charges on atoms. And I'll show you a really simple rule for that. And that is the formal charge is equal to your valence number from the periodic table minus your lone pair electrons minus 1/2 of your bonding pairs. So I think that's where we're going to stop today. Like I said, sometimes get very excited about organic chemistry and thought we would get further. That being said, the pod will not be due at the start of class tomorrow. Instead, we'll work on it at the start of class tomorrow. So don't worry about the pod. If you want to try to get a jump start on it, go ahead, but we'll work on it at the start of class tomorrow. All right, those of you in Monday lab, I'll meet you upstairs in a few minutes.